All right, it's brilliant that you're all here, and we're going to have a very exciting session. And it's going to be all about data-driven techniques, which is a cool buzzword. So the UK government gave loads of money to an institute on big data. And we're going to kick it off with a talk on STL validation with guarantees, and it's going to be given by Hendrik Röhm. Please.
So thank you. Hello, everyone. So one first question. Why are you all here? So, I guess you're all here for computer-aided verification. That's the title of the conference. And for verification, you need a formal specification. In our case, we use signal temporal logic. So it's a temporal logic, and we use that to reason about signals over continuous time and continuous value. So it's pretty important. It's quite different to the discrete thing you actually, I think most of you people work on. So here we have continuous time and continuous values. And if you have such a formal specification in STL, as a STL formula, we want to use that for verification purposes. And if we have done something and we verified something, the question is, are we done? And we are only done if we fully understand the formula phi we use for verification. And here, sometimes error happens. And with the tool STLInspector, we want to help to mitigate this kind of errors. So where does a formal specification typically come from? In our case, usually we have an informal textual requirement, and an engineer formalizes that to a formal specification that can be used for verification. So here I have one example. At some point in time, in the first 30 seconds, the vehicle speed well will go over 100 km per hour and then stay above the bound for 20 seconds. Now we can formalize that in STL formula. Here's one candidate formalization. I don't want to go into detail here. And the question arises here, does the formal specification, the formula, really fit to this informal artifact? We have to check that. Because here we also want to communicate the results to non-experts, and therefore we have to give them a confidence that we formalized the right thing. And usually you can't give them the formal semantics of the logic and just say, yeah, try to understand it. That does not work. So on the other hand, if you formalize that, even if you're an expert, usually there are some corner cases in this because temporal logic usually are not that easy. And such errors can happen fast, and we want to check that the corner cases are not bad. Because then you formalize something, and in the end you used it, and afterwards you think, oh, I missed something. Yeah, and you don't want to miss anything. All right. And this is what the tool STLInspector is about. It's a way of systematically validating the formal specification against this informal textual requirement, the artifact we have before. All right, some words about signal temporal logic. I think everyone here knows linear temporal logic, and signal temporal logic is basically the same thing, but for continuous signals over continuous time. So here I've brought an example. It's the velocity over time, and we have an atomic proposition. Velocity should be higher than a bound, and now we can evaluate this atomic proposition on the signal, and for some points in time it's true, for other points in time it's false. And here, what's really important is it's continuous time, so there are some difficulties compared to linear time where you have discrete steps. All right. Now we have atomic propositions, we can combine them. It's the same than LTL, logical operators and temporal operators. And here I've give some example. It's the finally operator, and compared to the discrete case, here we have time bounds. So here it says basically finally 1 to 42 seconds in the future, this atomic proposition should hold. So we need some peak here, but in this interval, one time in the future to 47 seconds. All right. If you talk about these formulas, usually we use examples. And because examples are simpler, we also try to use this level of, and not the level of abstraction or formal semantics to talk to people and to use it in the tool. And therefore, we use give a formula phi as input. We use a test generation algorithm, and then we generate test signals. These test signals are visually inspected by an engineer. So we use an engineer in the loop. And then the engineer says basically if the signal satisfies this informal textual requirement. And then we do a consistency check against the formal semantics of the formula phi. And in the end, if the consistency is there, everything is fine. But if not, we get a counterexample. And that's quite nice, because then we have one specific example where something happened, and we can investigate on this one specific example here. All right, so how does this test generation works here? We have a formula, and then we use formally defined mutation operators to mutate this formula. So here, for instance, that's one example. We have one formula, and we have one comparison operator, and we have this mutation operator that changes this comparison to another one. And then we have a formula. It's somehow the same, but one thing happened, and we have one fault in it. So now we want to generate one test that separates this formula from the mutant, and therefore we generate a test that satisfies the formula, but not the mutant. And therefore, we combine them, do a logical encoding by discretizing time, and then using an SMT solver set3 to generate one test out of this. All right, so this tool is written in Python, and you can simply install it right now. I see a lot of laptops here. You just go to the shell, type in pip install STLInspector, and it should magically appear on your laptop. If that does not happen, please talk to me. So afterwards, you can start it by typing in STLInspector and then the project directory where you want to save files. So I've prepared a short demo here. I already opened one project. So on the top here, you see the textual requirement we want to compare against. And here, this STL candidate I've shown you before. So then we have some results that are not shown right now, and here we have 4 tests. And I already prepared this because I've already looked on 3 signals, but one signal is missing. And right now we look on this last signal here to check if it's consistent or not. So now here we have this textual requirement we want to compare against and one test signal. And here you basically see it's toggling between 100 and 101 kilometer per hour. And now we have to check if this signal satisfies the textual requirement. But because the textual requirement states that the velocity should be higher for 20 seconds, and it's just higher for 10 seconds, the signal does not satisfy the textual requirement. And therefore, here I say no, it does not satisfy the requirement. All right, now we get 2 things. Inspection result differ from candidate for test, so we have an inconsistency. And second, we evaluated all tests, so we are done. So now we compare the results here. And as you can see, here 3 tests failed to be consistent and only 1. And therefore, we see that there's a problem here. And in fact, this formula here is a tautology. That's true, but a little bit different in writing here. And now we have to refine that and do that again. All right. So that's basically STLInspector, systematic validation with guarantees. We also checked it on data from a survey and found that we really find all problems that the people put in this formalization they did. So thank you very much.